Welcome. Welcome to the 2021 JMM Invited Address. It's a pleasure to welcome you here. It's a pleasure and an honor to introduce our plenary speaker today, Douglas Arnold. Professor Douglas Arnold received his PhD from University of Chicago in 1979. He held numerous positions, including academic faculty positions at the University of Maryland, at Penn State, and at University of Minnesota. At the University of Minnesota, he's right now the McKnight Professor of Mathematics, and he also served there as the director of the IMA, the Institute for Mathematics and Applications, from 2001 to 2008. He served in numerous distinguished service positions, including being the president of the SIAM, Society for Industrial and Applied Mathematics, from 2009 and 10. Doug is distinguished for his work. He is a fellow of the AMS, he is a fellow of SIAM, and he's also a fellow of the ASSS, so that's the Association for Advancement of American, I apologize, in Science. He's also a Guggenheim Fellow, and he's a foreign member of the Norwegian Academy of Sciences and Letters. Doug published over 100 papers, articles, and is also very active in editorial work. He is an editor-in-chief of SMAI, that's the French Society for Industrial and Applied Mathematics. He's also an incoming editor-in-chief of Acta Numerica, and he's also involved in a lot of other editorial boards and publishing, in particular of the communications of the AMS. He chairs the AMS Committee on Publications. For his incredibly distinguished service, he received numerous publications and involvement in a lot of different things. He received the SIAM Prize for Distinguished Service. Doug is incredibly passionate about everything he does. Probably people know him for that, both for his mathematics as well as the causes he supports. So it's an honor to introduce him, and I have a blurb to introduce this particular talk that he's giving today. He gave a plenary lecture at the ICIAM, International Congress of Mathematicians, in 2002, in which he first discussed this topic. He initiated the finite element exterior calculus, a new approach to the stability of the finite element methods based on geometric and topological structure underlying the relevant partial differential equations. So again, it's a pleasure to introduce Doug, and please let me welcome you again to this talk. Thank you. You can share your screen. Excellent, it works.
Okay.
Thank you.
Good morning. Thank you very much for that very generous introduction, and great thanks to the organizers and to the AMS for this opportunity, and to all the people who've gotten up early in the morning or something else in their time zone and have chosen to attend. So I'm going to talk today about the discretization of partial differential equations, so numerical analysis. But partial differential equations, of course, arise everywhere in modeling, in the physical sciences, in the biological sciences, in social sciences. And solving them is important to everything we do, many things that we do in society and technology. But you usually cannot solve a PDE exactly, and you're forced to get approximate solutions. And the basic process for this is taking that infinite dimensional PDE and reducing it to a finite dimensional problem that's in some sense nearby it, and then solving that finite dimensional problem on a computer. Each of those steps has many aspects and ramifications. And I'm going to be talking today mostly about a theme that's been grown to be very important in the last decades or so, called structure preserving discretization. But first, let me get some standard numerical analysis terminology. forward. So looking at things from a very high level, what you have is some operator L that takes a point of a space X to a point of a space Y. You pick a piece of data F and Y, and you try to solve LU equals F. So in the example of numerical solution of PDE, L will be a PDE. You also include boundary conditions and so forth. X is the solution space. Y is the data space. So when I say discretize, we're talking about replacing that with a finite dimensional problem. LH XH equals YH. So I replace the space X with some finite dimensional space and so forth. I pick a piece of data, discrete data FH, and I solve LH UH equals FH.
Doug, excuse me. Sorry for interrupting, but I think your slides are not moving. Attendees notice that as well. So you need to move your slides forward, please.
You're not seeing
no.
motion now?
Since you started introducing notation, it's obvious that they were not moving.
Can you see it now?
Nope, not yet. Just the first slide.
Is that the second slide?
Nope, still the first
then
one.
Let me try again. I will stop sharing and restart sharing. Okay, I'm sorry, I understand. Thank you very much. Here we go. So that was the first slide we were talking about, and you hadn't seen this before. You can see it now, right?
No, yes, we can see it now, thank you. Yes.
Okay, so we have this problem LU equals F, where L is an operator from one space of solutions to another space of data. And we discretize it by constructing an LH on some finite dimensional space XH. In practice, X would be a space of functions, and XH might be a space of functions on a finite dimensional lattice, on a grid. Or X might be a space, a finite dimensional function space made up of piecewise polynomials, as in finite elements. And of course, the question is the discrete solution you get out of your discretization, UH, is it close to U? So to make that precise, you have to define the error. That's the difference between U and UH. There's a small technical point. U and UH live in different spaces. So you take a representative of U called capital U in XH. That would be, for instance, taking a function and restricting it to the grid points. And then you measure that with respect to some norm, which has to be of relevance for your problem, some norm in XH. And convergence, of course, means that if you do this for a sequence of different grids, so let's say H going to 0, then the error converges to 0. And in numerical analysis, the main two things you think about when you think of trying to show that a method is convergent is the consistency, which measures to the extent to which the exact solution fails to satisfy the discrete problem. So this measures how well your discrete LH and your discrete data FH capture the true L and F. So LHU minus FH should be close to 0, and the difference is called the consistency error, and a method is called consistent if that tends to 0. And finally, the concept of stability, which is basically the well-posedness of the discrete problem. This only involves the discrete level, not the continuous level, measured by the norm of LH inverse as an operator from YH to XH. And stability means that doesn't blow up, that stays bounded. And if you define these three simple concepts, you very easily get the error estimate, that the error is bounded by the product of the stability constant and the consistency error. And consequently, you get a simple theorem that the discretization is convergent if the method is stable, so the stability constant doesn't blow up, and consistent, so the consistency error goes to 0. Okay, so those are the things that one usually deals with, and it can be very difficult to design a discretization that's both consistent and stable. That's what numerical analysts do. But I want to talk particularly about structure preservation, which is a different concept, and it's become increasingly a tool that allows us to get stable and consistent methods in situations where we didn't know how to do it before. I'm going to talk about it for PDEs as the main theme of the talk, but first let me try to illustrate by the simpler case of ODEs, where there are some very well-established structure-preserving discretizations, one of which I'll talk about, symplectic integration. So by structure-preserving discretization, I mean that the numerical method should preserve on the discrete level some key geometric, topological, algebraic structures that are possessed by the original system. So some key structures should be exactly maintained, not approximately, not measured going to zero, but should be exactly maintained. And the most classical example perhaps is the symplectic integrators for a Hamiltonian ODE. So I'll say what that is, but first let me show it to you in action on a very simple example. Suppose we take Kepler's equations. So basically we have a fixed body, the sun at the origin, and we have a body x moving on some orbit x of t through space. And we have Newton's equations of mechanics, x, the time derivative of velocity of position is velocity, and the time derivative of velocity is negatively proportional to the position vector times 1 over the, with a magnitude of the reciprocal of the square of the distance, the inverse square law. So now I'm going to approximate that PDE, that ODE, using Euler's method. So Euler's method is written down here. Instead, all we do is instead of x dot, the time derivative, we take x at different time steps, first time step, second time step, and we take a finite difference, xn plus 1 minus xn over h, to approximate the derivative. That introduces a consistency error of order h, where h is the time step. And we do something second with the second equation with the inverse square law, so that we have the approximation of the derivative of the velocity is the inverse square force. And I run this with many, many time steps, say 200,000 time steps for 4 periods of the orbit. Here, the green is the exact solution. So the green dot is at both the initial data, where the planet starts out, and then it goes on this green orbit 4 times and returns to where it started. That's, of course, the exact solution of Kepler's equations, is that ellipse. And we see that the red dot shows the solution to Euler's equation with these 200,000 time steps. And we see that that wanders off the orbit quite significantly. So by the time you get to 4 orbits, you've got completely garbage results. The planet is in entirely the wrong position and not even close to the true orbit anymore, or not very close to it. So now I show you a symplectic integrator. Euler's method is not a symplectic integrator. There's something called the symplectic Euler method, and the difference is very slight. All we do is in the inverse square law in the second equation, after having determined xn plus 1 from the first equation, we determine vn plus 1 using the new xn plus 1, rather than using the old xn. That method is a symplectic method, and you can see from this picture it does infinitely better, so you can almost not distinguish the red approximation from the true green. You can see here there's a tiny little phase error, so there is some error with 200,000 time steps. Of course, Euler's method and symplectic Euler method have a large consistency error, only proportional to the time step, and wouldn't be practical for significant problems. But what you do is there are higher order methods that behave similarly. So instead of Euler's method, you could use the classical Runge-Kutta method, which has a consistency error of h to the power 4. And there's also a symplectic 4-stage method called the Gauss-Legendre method. So here on the left, I show the Runge-Kutta method. And what you see, all this filled in area, is the discrete planet, the Runge-Kutta method, spiraling in and wandering off the orbit. So that's a failure of the classical 4-stage Runge-Kutta method, even with 1,000,000 time steps. On the other hand, the Gauss-Legendre method you can't distinguish from reality, even after 1,000 periods. So it makes a big difference, this symplectic integration. That's the takeaway message there. And here are some of the references. These ideas first appeared in the 80s, got a huge boost theoretically and in our understanding from Jesus Sancerna in the 90s, and many other people are involved. And there's even an excellent textbook that covers this kind of stuff by Harris, Lubish, and Warner. Let me give a realistic example instead of such an academic example. This is from a 2009 paper by Jacques Lascar and Michael Gastineau. And they simulated not just one planet, but the entire solar system, and not just for a few orbits, but for 5 billion years. Now, in order to know where the solar system is 5 billion years from now, you have to know its initial position now very, very exactly, more exactly than we do. So the way they did this is they did a statistical study. They varied the initial data by fractions of a millimeter and did 2,500 different tests. And here they're showing the orbit, they're showing the eccentricity of Mercury as it varies over 5 billion years for all 2,500 tests on one graph. And what you see is some of them blow up. So what they found is 1% of the simulations resulted in unstable orbits where the solar system would basically crash. So the question I want to ask is, how did they compute for 5 billion years? What kind of numerical method did they use? And of course, symplecticity was key to that. So now let's say, what do I mean by symplectic integrator? Well, the Kepler problem, the n-body problem, the harmonic oscillator, the pendulum, electromagnetic problems, et cetera, et cetera, et cetera, they're all Hamiltonian systems. They have the form of the PDEs I've written there. They can be written in terms of one Hamiltonian function, h, of two sets of variables, the position variables p and the momentum variables q. To say it's a Hamiltonian system, another way to say that is that the map in phase space that maps PQ at the initial time to PQ at some forward positive time is a symplectic transformation, which it means that the differential two form dp1 d wedge dq1 plus etc., that differential two form is invariant under the flow. So what does that mean? It basically means that the flow is volume preserving in phase space. It precisely means that in two dimensions. It's a little more complicated in higher dimensions. Here I've drawn the phase space picture of the pendulum equation. Q dot equals P, P dot is minus sine Q. That's a Hamiltonian system with the Hamiltonian I indicated there, and it gives rise to this phase space picture. Now choose some initial data. Here I've chosen three little regions of phase space for initial data. So look at the red one, for instance. Any point in that little box could be a piece of initial data, and we move it forward and we get to another little region of phase space, which I've shown here. And we could do that more and more and more and more and more and more. And what you notice is that the phase space is getting highly distorted by the flow. However, it's getting distorted in a volume preserving fashion. That's the essence of symplecticity. Now let's talk about a discretization. So that was the structure of the true problem, the true ODEs. Now we talk about the discretization where we get discrete solutions P and Qn at different time steps. And we look at the transformation determined by the numerical method that gets us from one time step to the next. And a discretization is symplectic if that's a symplectic transformation, basically if that's volume preserving in phase space. But it has to exactly be symplectic, not order h to the r. So that's what I mean by a structure preserving discretization. It takes that structure, symplecticity, and preserves it exactly. And these two pictures here show that the Euler method is not symplectic. You can see that the small red box got distorted into a bigger red box by taking a time step, while the symplectic Euler method is symplectic. And this led to a large enterprise to try to develop methods to come up with symplectic numerical integrators, which were high order, that means small consistency error, low cost, high robustness, and all sorts of other desirable properties. And now there are many strong, powerful symplectic integrators known. There's also a theory about why symplectic integrators work and trying to prove that you get those good behaviors that I showed you in the numerics. One of the key tools is backward error analysis, where people look at a integrator. So here's one orbit from the pendulum equation in blue, and the corresponding orbit from Euler's method are the red dots. And backward error analysis doesn't say how close are the red dots to the blue? What that says is, what is the red dot solving? What is giving us that spiral? And you can do that computation, and you see instead of solving q dot equals p, it solves q dot equals p plus h over 2 sine q, a small perturbation. And similarly for the second equation. And the problem is that not only is that a small perturbation but of the original system, but the new system is not symplectic, and it has those spiral dynamics. By contrast, for Euler's method, the new system has one sign different, otherwise it's the same. It's a small perturbation again, but it's also symplectic, so it has Hamiltonian dynamics, which means there are no spirals, that it has Poincare recurrence, that there's no dissipation, and so forth, closed orbits. And now let's go back to the real problem we talked about by Lescar and Gastineau. So how did they simulate the solar system for 5 gigayears? What method did they use? They used one of these sophisticated methods that's been developed in the 90s, called SABA4 by McLaughlin and Lescar and Robitaille. It uses fancy Lie theory for the derivation. It's symplectic. It also preserves other structures like time symmetry. They did 200 billion time steps of step length 9 days. And then if you ask, what about the consistency error? Surprisingly, it's only second order. And that was puzzling, except that it does something else. It exploits the fact that the n-body problem for the solar system is a perturbation of n uncoupled Kepler problems. That is, the interplanetary attraction is very small perturbation compared to the solar attraction. And the true consistency error of SABA4 is h squared, the time step squared, times epsilon squared, where epsilon is the ratio of planetary mass to solar mass, and so very small, plus another term, which is epsilon h to the 8th. And this is the very small consistency error that allowed them to get accuracy with over such a long period of time. Okay, so that was sort of an introduction to structure preserving discretization. And now I want to talk about what can we do for PDEs. And I'm going to talk about one particular structure preserving discretization, the one that I'm most involved in, the finite element exterior calculus. So let me go to examples. They're somewhere between true physical examples, but pared down to fairly academic prototypes of them so you can see what's going on. So the first example is Darcy flow, which is one of the fundamental flow models of physics. Darcy flow describes the motion of a fluid like water through a porous media like sand. So here, for example, is a sandy region, and we are injecting water in the upper right corner, and it's flowing through this, and we're extracting water at the lower left corner through some sort of extraction well. The equations are, there's a velocity vector field, which is negatively proportional to the pressure gradient. The pressure is a scalar function. So you flow against the pressure gradient, and then the divergence of the velocity is any sources and sinks F. The F would take into account the wells here. This is saying that fluid is not, well, first of all, the fluid is incompressible and no fluid is lost. Okay, to discretize a system like this, since I'm using finite element methods, you don't work directly from this strong form of PDEs. You always, in the finite element method, put the equations into a weak form. So for example, take the second equation, div v equals f. You take an arbitrary test function q, multiply the equation by q, and integrate it over the domain. Here I'm using the L2 inner product to write the integrals. So this is the integral of div v times q is equal to the integral of f times q for all q. And that's another way of capturing the second equation. The first equation is similar. We multiply by A inverse W, where W is some vector field. And when we do the integration of the gradient of P on W, we integrate by parts, so we get P div W. Then starting from that weak form, the finite element method determines the discrete solution by restricting the space of all vector fields V and all scalar fields P and all vector field test function vector fields W and all scalar test functions Q, they restrict those to finite dimensional spaces. So that's discretization. And the last question is, what spaces can we use in order to get a method with a good consistency error, small consistency error, and which is stable? And the stable is often the difficult part to do this, and you'll see that in a minute. So what spaces to use? The basic idea of the finite element method is that you get your spaces by triangulating your domain and using piecewise polynomials on each subject to that triangulation. If you've taken only one course in finite elements and you saw this problem, you'd know immediately what spaces to use. What the first thing that would jump to your mind, you'd look at these equations and say, well, Q in the weak form is never differentiated, so I can use the simplest possible piecewise polynomials, just piecewise constants would be the simplest thing. And that's shown on the bottom line here. This notation where I take a triangle and put a dot on it, what I mean is that the domain is triangulated into triangles, and on each triangle I specify one number, which is the value of the piecewise constant on that triangle. But then the person who's taken one finite element course looks again at the weak formulation and sees a derivative on the V, and therefore they can't use discontinuous functions like piecewise constants, so they take the simplest thing that gives you continuous piecewise polynomials, namely piecewise linear vector fields, and those are specified by given the two components of the vector field at each of the three vertices of the triangle. That would be the standard finite element approach. And for many problems, this is a highly successful method, and that's why it's the standard approach. But this is not one of those methods. This method is a complete failure for Darcy flow. So here I did the computation with some sort of typical triangulation with a few hundred triangles. And if you're a numerical analyst, you look at this picture and you see immediately instability. What you're seeing is this is the pressure field, which was a piecewise constant. So each triangle is colored according to the pressure. Green is 0, blue is very low pressure, negative 100, 1,000, and red is very high pressure. And what you see is as you go from one element to the next, there's an oscillation, high pressure, low pressure, high pressure, low pressure. That's completely unphysical. It can't be the right solution. What is the right solution? Well, I'm going to use a good numerical method to compute it, namely FEAC, finite element exterior calculus approach. This would really be called mixed finite elements. Again, I'm using, it has a funny name in FEAC, but these are just the ordinary piecewise constants. And again, I'm showing you the pressure field. So it's piecewise constant, but now you have a reasonable transition from a pressure of positive 30 to about minus 50, something like that. It's not a super accurate pressure field, but that's because the consistency error is not very low, because we only use piecewise constants and piecewise linears, which lead to a consistency error of order H. If I take a higher order FEAC method, using instead of piecewise constants for the pressure, piecewise linears, and instead of piecewise linears for the velocity, a more sophisticated space. This FEAC space here, which I'm not going to explain yet, is a more sophisticated space than just the space of all polynomials. It lies somewhere between piecewise constants and piecewise linears, and somewhere between fully discontinuous and continuous. It was invented, they're called the Ravier-Thoma elements, invented in 1975, and immensely important. And actually in the 1990s, it was realized that they weren't invented in 1975. They already appear in Whitney's book on geometric integration theory in 1957, not for numerical purposes, but as some sort of natural way to define a discrete differential one form, which is what they are. Let me show you this is the same computation done with higher order FEAC elements. And then you see a very smooth transition in the pressure field. And if I showed you the exact pressure field, you wouldn't be able to see the difference. So that was example 1. Example 2 is an eigenvalue problem. So it can be written in either vector calculus notation. We're looking for a vector field U and that satisfies curl U minus grad div U equals lambda U. Or we can write it in the language of differential forms, in which case it's just the Hodge-Laplacian eigenvalue problem. D star D plus DD star applied to a one form U is lambda U. In either case, we could put it into this weak form. That's one possibility. And I'm going to do the computation on this sort of asymmetric square annular ring. So what I'm going to do now is I discretize by triangulating this domain and using standard continuous piecewise linear finite elements. And I'll compute the first three eigenvalues of that finite dimensional system. The eigenvalues are 1.94, 2.02, and 2.26. And the eigenvectors are pictured here. That's using standard piecewise linear finite elements. Unfortunately, again, that answer, it looks pretty. You don't see an obvious instability, but it's totally wrong again. Here's what phi gives you. This is the correct answer. And the first eigenvalue is not 1.94, it's 0. And that's something we can actually check analytically. If you know anything on Hodge theory tells us that if you have a non-simply connected domain, the Hodge Laplacian has a kernel whose dimension is the first Betti number, the number of holes in the domain. So that means the lowest eigenvalue of the Hodge Laplacian on this domain is definitely exactly 0. It can't be 1.94. The other ones turned out to be completely wrong as well, and the eigenvectors wrong as well. This situation is actually worse than the Darcy flow problem because it's hard to see the instability. This is a picture of the first 6 eigenvalues computed using standard finite element method, using first a triangulation of 64 triangles, then 256, then 1024, all the way up to 1,000,000. And you see all 6 eigenvalues are nicely converging, and that might give you confidence, but it's misplaced confidence because the thing they're converging to is nowhere near the true eigenvalues. They converge to something that's totally wrong. If you do the same computation with phi, they converge also nicely, but they converge to the right answers. And finally, one more example why we need to have a finite element exterior calculus. This is another eigenvalue problem, but now I leave off the d star terms. So this is the curl-curl eigenvalue problem, very important in electromagnetics, called the Maxwell eigenvalue problem. You solve it with standard finite elements, and I'll do this one no holes, so this one doesn't have to do with topology. I'll just do it on the square, where I know the exact eigenvalues. They're the sum of the squares of natural numbers, m squared plus n squared. So the first one is 1 plus 1 is 2. The next one is 4 plus 1 and 1 plus 4. So there's a double eigenvalue at 5, etc. And here we see it. I compute on meshes like the one shown with 16 elements, 64 elements, up to 4,000. And you see, indeed, the first eigenvalue is converging nicely to 2 with standard finite elements. The second eigenvalue is converging nicely to 5, the third to 5. The fourth is converging nicely to 6. But that's a bit of a problem because 6 is not the sum of 2 integers squared. It's not the sum of 2 squares. So this is these red circled eigenvalues are totally spurious coming from the normal finite element method. We do the same computation with phi and we get exactly the right results without any problems. Nice convergence. Okay, so that gives you 3 examples where you need a structure preserving method. You need the finite element exterior calculus to get a good stable numerical method. This has developed by now into a theory. I released a book on it in SciAm at the end of 2018, which is probably the easiest reference at the moment, although a major paper in it was by myself, Falk, and Winter in the bulletin of the AMS in 2010. That's another possible reference. The structure which is preserved in phi is called a Hilbert complex, and its resulting cohomology in Hodge theory. And so the idea of phi is to design discretizations that reproduce the Hilbert complex structure and the related structures at the discrete level, and in that way achieve stable, consistent, and so convergent numerical methods. So what's a Hilbert complex? It's an interesting story. While we were developing phi theory, we invented Hilbert complexes, and we also invented the name Hilbert complexes. And then as we were writing things up for the bulletin, we did our due diligence in studying the literature, we found that the exact same concept was already invented, and it was already called the Hilbert complex. So the credit for the Hilbert complexes goes to Bruning and Lesch in the 1990s. And here's the definition. You have a sequence of Hilbert spaces, W0, W1, it's usually some finite number, and then there's zeros after that. And from one Hilbert space to the next, you have an operator D. It's a linear operator, but it doesn't have to be bounded, and it doesn't have to be everywhere defined. It's the more general notion of a closed, densely defined operator. So it has a domain, that's what I denote by V, inside W, which is the dense subspace of W, and D is a closed operator mapping that space into W. And it should make a complex so that the range in one D is inside the null space of the next D. And the other important property is that the Hilbert complex be what I call closed, which means not that the D's are closed operators, but that the ranges of those operators are closed subspaces of the W's. So here's the example to have in mind, and it depends on your background whether you like to think of this in exterior calculus terms or vector calculus terms. Here it is for vector calculus in R3. The first Hilbert space is just L2, and the first operator is the gradient. And then the second Hilbert space is L2 vector fields. And of course, not every L2 function has a gradient in L2. The space of functions that do have a gradient in L2 is the Sobolev space H1. So that's the domain of the first D. Then the second D similarly is the curl. Its domain is everything whose curl is in L2. The third D, that maps also into vector fields. Then the next space would be scalar fields again, and the operator would be the divergence. So we have grad, curl, div. Of course, that can be interpreted in the language of differential forms. These are really L2 differential 0 forms, and then the exterior derivative takes them to L2 differential 1 forms, and the exterior derivative takes those to L2 differential 2 forms up to differential n forms in n dimensions. So that's a Hilbert complex. It's a simple definition, but it has many, many ramifications. So every closed Hilbert complex, well, it's a complex, so it has cohomology. But it's also Hilbert space based, so the cohomology can be realized as concrete harmonic forms. That is to say, the null space modulo the range can be replaced by the orthogonal complement of the range inside the null space. Those are called the harmonic forms. That's the essence of Hodge theory. In addition, a closed operator on Hilbert spaces has a dual operator, an adjoint operator going back the other direction. And so every Hilbert complex has a dual complex with D stars going down in index. And duality tells us that the orthogonal complement of the null space of D is the range of D star. There's a Hodge decomposition for every Hilbert complex. Every one of these spaces W can be split up into the range of the incoming D, the range of the incoming D star, and the harmonic forms, and that's an orthogonal decomposition. There's also a quantitative inequality associated with the complex at every level. You can bound U by bounding D of U as long as U is orthogonal to the null space of D. That's called the Poincare inequality. And there are many more properties. And these are the properties that, well, okay, I need to now get a operator out of this. Once I do that, and I'll do that on the next slide, these are the properties that tell us the operator equation, the LU equals F, is well posed. In fact, that's why these kind of theories, these Hodge theories, were invented, to show the well-posedness of PDEs. So there I've summarized the key essence in 3 of the spaces of a Hilbert complex with the 2 Ds and the D stars going backwards. And for every Hilbert complex and any K, we can create an operator, and the operators just start at a point U and W, do D and then D star, so D star D, and add that to what happens if you do D D star. And that sum is called the Hodge Laplacian, and that's a closed densely defined operator from W to itself, WK to itself. And for every Hilbert complex in every K, that's a well-posed problem exactly up to the harmonic forms. It has an obvious weak formulation, which was the one that I used previously when we looked at the eigenvalues of this problem. And it also has a mixed weak formulation. And this is the one that turns out to be much better for discretization. This is what Feek uses, while the method that failed utterly used the one in green. The mixed formulation, you introduce a new variable, sigma, and you can see from the first weak equation that sigma is just d star u. This is actually the definition of d star u, is this equation. And then the second equation says that d sigma, so d star u, plus d star du is equal to f. So this is a different way to formulate the Hodge-Laplacian problem, d star plus d star du equals f. Now that's the way to get a PDE, or more generally an abstract operator equation, out of a Hilbert complex. You get a Hodge-Laplacian. Another thing you can do is you can get a Hodge wave equation. For that, you look at functions capital U, which depend on t and map into the spaces W. So at every time t, U of t is an element of some WK. And you ask that the second time derivative of U plus the Hodge-Laplacian of U is 0. That's what I call the Hodge wave equation, together with initial conditions. I've written that in strong form using a matrix notation here, introducing new variables d star u and du, somewhat analogous to these red equations on the previous slide. And I can also, in a similar way, write it in weak form using those variables. And this is also a well-posed problem. So for any initial data, it's well-posed and gives you a solution of the wave equation. So these are examples of problems that you can solve using Hilbert complexes. By the way, a specific example of the Hodge wave equation, if I take a specific Hilbert complex, are Maxwell's equations. Here are Maxwell's equations as you'll see them in an electromagnetics textbook. There's 4 variables, the electric field E, the magnetic field B, the electric displacement D, and the magnetic intensity H, and 2 material parameters, the permeability and permittivity, epsilon and mu. And what you do is you make 3 Hilbert spaces, L2 scalars, L2 vectors with a norm weighted by epsilon, and L2 vectors with a norm weighted by U inverse. And then you take with those Hilbert spaces, something that looks like a piece of the de Rham complex, gradient and minus curl. And if you write down the Hodge wave equation for this Hilbert complex at the level W1, you get this system here. It has 3 variables, E, B, and also something called sigma. And the theorem says that if your data is compatible with the divergence constraints here, and your initial data for sigma is chosen to be 0, then sigma is 0 for all time, and E and B are the solution to Maxwell's equations, and D and H can be defined from them. So Maxwell equations are perfectly captured by the Hodge-Laplacian, and if you want to prove their well-posedness, it would just be this theorem about the Hodge wave equation, I should say. Okay, so that's the structure that finite element exterior calculus is trying to capture, and now we get to discretization. So the question will be, if I have a Hilbert complex, how do I find my finite element subspaces such that it also has a Hilbert complex structure at the discrete level? So let's talk a little bit again about discretization. So we have these 3 Hilbert spaces that enter the weak formulation. We're going to have to pick subspaces. So, and they're going to have to be in the domain of D, so subspaces of the V spaces. VK is the domain of DK, and we choose a finite dimensional subspace of it. In practice, VK will be a space of functions or differential forms, and VKH will be a finite dimensional piecewise polynomial space of functions or differential forms. Well, so after a long story, one of the crucial conclusions of the Feek theory is that for the discretization to be both stable and convergent, you need 2 crucial conditions to be satisfied by the space choices. One is the subcomplex property that D of VKH should be contained in the next space, VK plus 1H. That means that the VKH spaces form a subcomplex of the original complex of the V spaces. And it's not enough that you have, so that's enough to give you a Hilbert complex on the discrete level. And this bottom complex is a Hilbert complex. And you have the original Hilbert complex on the continuous level on the top. But that's not enough. You also need a relationship between the two, and that's given by bounded cochain projections. So the second key hypothesis is that there exist projection operators mapping VK down to VKH from the continuous level to the finite dimensional discrete level. These are projections. They commute. They're cochain operators, so d pi is equal to pi d. And they're bounded operators on the V spaces, so bounded cochain projection operators. And one of the fundamental theorems of Fick is that when the subcomplex property and the bounded cochain projection property hold, the discrete spaces themselves form a Hilbert complex. And the discretization of the Hodge-Laplacian using these spaces is exactly the Hodge-Laplacian associated to the discrete Hilbert complex, because every Hilbert complex has a Hodge-Laplacian. And so this discrete Hilbert complex has its own Hodge-Laplacian with its own D and its own D star and so forth. And what's more, the projection operators induce an isomorphism on the cohomology of the top complex to the bottom complex. What that means is that we'll never see that problem with the missing zero eigenvalue we saw when we used the ordinary finite elements. They miss the cohomology. But this says that if you have these two conditions, you'll never miss the cohomology, you'll get it exactly right. And then pushing things a little further, you can use these ideas to show that you have use things like the discrete Hodge decomposition, the discrete Poincare inequality, and you get stability and convergence. And so this is really a prime example of structure preserving discretization. By preserving the structure, you get a stable convergent numerical method. Okay, so that is the abstract theory, the key aspects of the abstract theory of finite element exterior calculus. If you have a problem like a Hodge-Laplacian or a Hodge wave equation coming from a Hilbert complex, if you can choose subspaces of the spaces in the Hilbert complex which satisfy the subcomplex property and the bounded cochain projection property, then you'll get good discretization. And so that leaves a key challenge, which is to construct the finite element spaces that satisfy these conditions. Now, what does it mean to construct a finite element space? Well, this really can't be done in the abstract on all the complexes at once. You have to look at each individual complex. If we have a complex made out of function spaces or differential forms, what we have to do is first cut the domain into pieces. And so we have to specify what kind of pieces we're going to use, for example, into triangles or squares or simplices or cubes or higher dimensional analogs of those, or maybe polyhedra, for example, is getting very popular. Then, having specified a triangulation of sorts, the next thing is to say what kind of functions you're going to allow on each triangle. Those are called the shape functions on the one particular triangle or the one particular element. And those are typically polynomials of a certain degree, but not necessarily a complete polynomial space. And sometimes a lot of cleverness has to be invoked in order to define those. It's turned out that the Kazul complex has played a very big role in defining the right polynomial spaces, but I don't have time to get into that. And then the last thing is to specify what are called degrees of freedom. What these are there's one of them for each dimension of the space of polynomials you're using, and they're associated to the faces. So here I've put 3 on each edge of the triangle and 3 in the interior of the triangle. So there are 12 altogether. And I've used the space of polynomial of degree 2, 1 forms. That's a 12-dimensional space. So I have the right number of degrees of freedom. And I won't tell you exactly what these symbols mean, what kind of degrees of freedom, but they tell you how the piecewise polynomial, how the two polynomials from one triangle to the next have to connect. So they specify the continuity of the piecewise polynomials. And this was all one long sentence that we have to, a key challenge is to specify these three quantities in order to ensure the subcomplex and bounded cochain projection properties. And as I say, that's quite a challenge. That was a big part of getting feet going. For the Durham complex, it's now been done quite systematically and quite completely. So if we're using a space of finite element differential forms, we know what kind of discrete differential forms to use. And in fact, they've even been organized, this is work I did with Anders Log, into a periodic table of finite elements. Quickly describe what's in this table, and you can pick up the table and play with it yourself at that URL. I'm showing here dimensions 1, 2, and 3. The first 3 rows are dimension 1, the second 3 rows are dimension 2, and the last 3 are dimension 3. This picture could keep going. We could have dimension 4, 5, and 6, and so forth. In each row, I have 3 sub-rows. Those are the polynomial degree, which tells us the consistency error. So there's degree 1, degree 2, and degree 3 in each row shown in each dimension, and that could also be continued, so we could have any polynomial degree. Then the 4 major columns, well, the last 2 columns are for squares and cubes shaped elements, and the first 2 columns are for triangles, tetrahedra, simplices shaped elements. Within the reason there are 2 columns for simplices is there are 2 major families of finite elements using simplices and 2 major families using cubes. That's what we discovered. And finally, within each one, in 2 dimensions, we have 3 columns. Those correspond to differential 0 forms, differential 1 forms, differential 2 forms. In 3 dimensions, you also have differential 3 forms, so you have 4 columns and so forth. And this whole table of elements can be generated systematically, and sort of their properties obtained all at once. As I say, the Kazul operator is very important. This shows you just one of the elements. This one is this one over here, I think. And it specifies the element shape, the shape functions, the degrees of freedom, the total number of degrees of freedom, which is sort of the atomic number of the element. The name, we call it in the systematic Fichte derivation, P2 lambda 2 delta 3. And then it turned out that this element was long known, goes back to Nedelec in the 80s, and its traditional name is the Nedelec face elements of the second kind of degree 2. This periodic table takes many elements that were known and a few that were not known previously, and shows that they're all systematically derived by the same principles. Okay, and the last topic I want to discuss is much more current, bring this up to date, moving beyond the Durham complex. So for other PDEs, we need other Hilbert complexes. And for those, it's often not at all clear what finite elements to use. And this, in fact, was one of the big first successes of Fichte, was in the question of solving the elasticity equations. So the elasticity equations are the most important equations of solid mechanics. And they were one of the reasons finite elements were invented by engineers, or I should say reinvented, because mathematicians had gotten started earlier, but reinvented by engineers in the 1960s to solve the elasticity equations. And what are called mixed finite elements for elasticity are something that were sought from way back from the 1960s, but nobody was able to come up with them. They couldn't find the right piecewise polynomials. And this was answered by Fichte using the complex that's shown at the top of the screen here. This is what I call the elasticity complex. Instead of starting with scalar fields, it starts with vector fields. And instead of taking the gradient, it takes this deformation operator, which is the symmetric gradient. And so that takes a vector field and gives you a symmetric matrix field. Then the next operator is something called, is the linearized Einstein curvature. It's also called the Saint-Venant tensor and has some other names. This is the operator that you take a symmetric matrix field, you take the curl of every row, and then you take the curl of every column. And that second order operator gives you another symmetric matrix field called the incompatibility. And then the final operator takes a symmetric matrix field to a vector field by taking the divergence of every row. Looking at the Hodge-Laplacian and the Hodge wave equation and similar operators for this complex, depending on which level you get different operators. In particular, down at the right end, you get the mixed elasticity equations, which is the one that people wanted to solve for many purposes. Now people are looking at some of the earlier ones. You get dislocation equations and other equations relevant to relativity. And I won't go into the long story, but if you use standard finite elements, you get these kind of unstable solutions like we saw for Darcy flow, also here for elasticity. If you use the Fick elements, you get these beautiful, nice pictures of the stress coming out of elasticity. So the idea was to try to do this in some sort of more systematic way and with more, oh, and I see I'm running out of time, so I gotta finish this up.
A bit, yes.
So I will take 1.5 minutes. Looking at some other complexes. So here's another complex, the Hessian complex, that arrives in plate equations and relativity. And they all, these two and many others can be gotten by a general construction that starts with two complexes, puts in some connecting maps, reduces the spaces that are used, and splices them together. I don't have time to go through this, but let me just show you. If these are de Rham complexes with Sobolev regularity of varying degrees. The first one is scalar de Rham complex. The second one is a vector valued. The third is vector valued. The second is scalar valued. Out of these, we can pull all sorts of new complexes. That's the Hessian complex. That's the elasticity complex. That's the div-div complex. That's the grad-curl complex. That's the curl-div complex. They can all be related to the de Rham complex. And the last thing I was going to talk about, but I didn't leave myself time, was using the structure preserving discretization idea to do the same thing on the discrete level and go from known finite elements from the de Rham complex to new finite elements for the elasticity and other complexes. And I will stop here. Thank you very much for your attention.
Thank you. Thank you, Doug. I will clap for all of the attendees. Thank you very much. All the attendees, we do have time for questions. Please type them into the Q&A box. I will be moderating this Q&A session, so I will just take the questions as they come. And Doug, we have the first question from Peter DeLong. He congratulates you on the talk and asks the following question. How easy is it to add sources, currents and charges, to the discretized Maxwell equations?
I think that's not a problem. I mean, there's both the question of applying sources like additional currents and things like that, and also the question of the constitutive equations. I wrote down the equations for a dielectric, but more complicated things. I can't say that all cases are taken into account, but these ideas are used in many, many contexts, and I think usually they can be taken into account in these formulations.
Okay, thank you. We're waiting for more questions to be submitted online. Meanwhile, let me ask a question. So I was wondering about the developments in I guess over the last decade when people are trying to mix dimensions. So let's say you have like a Darcy equation in a 3D domain, and then you have some kind of a fracture or some kind of a surface on which you're posing another PDE. So, you know,
I remember that
with other discretizations that would be XFEM or something like this, when people are trying to work in mixed dimensional setting. Is there any hope for, you know, or do you need to match the spaces and the de Rham complexes individually between them, or what would you do?
Yeah, I'm not going to go out on a limb and say how well that's going to work. I think that's probably a natural question, but I'm not sure, and I can't draw to mind anybody who I know for sure is working on those kind of multi-structures, multi-dimensional structures. But it seems to me, if you're trying to do something like, well, I don't know if that method was used for something like Darcy flow. It certainly was used for elasticity. If you're trying to do, suppose you're trying to do something like incompressible elasticity, that forces you to use this approach, and traditional approaches to elasticity don't work very well with incompressibility. So if you're trying to do that in the context of those multi-structures, you need to figure out how to incorporate these ideas for it to work. But I'm not going to make a conjecture.
Okay. I will continue maybe asking my own questions later if there's still time. I would like to move on to the next question by Jean or Jean Lubuma. The question is, thank you for an excellent lecture, and how do you apply this FEEC to evolution PDEs?
Well, I did give the example of the Hodge wave equation, and there's in a similar sense a Hodge heat equation. So basically, the approach that we've used so far is to separate space and time. So you discretize the spatial dimensions using the FEEC ideas, and you discretize the time dimensions using ordinary finite different time stepping methods, ODE solver ideas. There hasn't been so much interaction, but an obvious idea is to, since there is well-defined, well-developed structure preserving discretization method for ODEs, to try to bring these two ideas together. There have been several programs at math institutes, probably most recently at the Newton Institute, on exactly that subject, bring together structure preserving discretizations for ODEs and PDEs. And one place where it looks like it's very appropriate is in trying to solve the Einstein equations. But I think we're in the middle of all this with people putting forth interesting ideas, but things not fully worked out yet. The behavior of the time dimensions is sort of very different than the behavior of the space dimensions. You can't treat hyperbolic problems like you treat elliptic problems, so you can't forget about the time discretization aspects of it. And as I say, so far, what's been most successful is separately discretizing in time and space. But it is very natural to do. It's very natural to consider, say, a differential form that depends on time and is a differential form in space.
All right, thank you. I have another question, and it sort of is a pedagogical question. Do you advocate then, as we're looking forward in the next 20 years of numerical analysis teaching, that we teach numerical analysis differently, and that we emphasize the structure preservation right there at the beginning, rather than as a follow-up at the counterexamples, like with the examples you started?
I would say that numerical analysis, sort of early on, and especially as the finite element method grew in the 60s and 70s, they realized that there was a great deal of functional analysis that was very relevant. And we started teaching all our students functional analysis and Sobolev spaces, and they become experts on this if they want to become theoretical numerical analysts. We didn't do the same for the geometry, and there's a huge amount of geometry and topology that's very relevant. And that's what I was emphasizing. That's what I was emphasizing here. And I think that is important to teach to students. It is important that they don't get this idea that in applied mathematics and numerical analysis, there's some pieces of math which are of interest and valuable, and the rest of math has nothing to do with it. It's not like that at all. So I do think there should be changes to the pedagogy.
Okay. Thank you. So we're close to being finished. I'm waiting still to see if there's some further questions in the Q&A box. If you would like to submit some attendees have been putting in items to the chat, but the Q&A is perhaps a more easy place for us to use. Let me ask Doug another question. You started with the Darcy equation. And if you think of the, let's say, nonlinear version of it for the multi-phase flows where you have the genericity, so evolution equations with lots of nonlinearities, do you see any challenges in applying and using the formalism of Fick for evolution equations where you have both the genericity and some kind of singularity in the evolution equation?
Those issues and nonlinearity in general bring up additional challenges. They're challenges that we, for the most part, know how to handle. I don't think they change that much when you're dealing with Fick. So all the examples I gave were linear, but what would happen if instead of looking at Darcy flow, we had some nonlinear terms in it, or we started looking at Navier-Stokes flow, for instance, instead of Stokes flow? Well, we know that what you have to do is you do linearization and use Newton's method, and then you make it more efficient with quasi-Newton methods and so forth. And this is pretty much understood. Of course, it doesn't make the deep issues of nonlinearity, like we don't even know existence of solutions to Navier-Stokes equations.
Yeah, sure.
It doesn't make those problems easy. Those problems are naturally hard, and this theory is not going to help solve them. But combining those ideas, the ideas that we have from dealing with nonlinear problems and singular problems with Fick, I think that's very much doable, and in many cases has been done already. And so, for instance, new Fick elements are being what I would call Fick elements, elements that have a Hilbert space, Hilbert complex structure underneath them, are being used for Navier-Stokes already.
Okay. Thank you very much for all the answers and for the wonderful talk. There were a lot of kudos also submitted by chat, so thanks again. I think at this point, I will clap and thank you again for all of the attendees, on behalf of all of the attendees, for the wonderful presentation and the answers. And we'll conclude the talk. I think our Convex folks will probably very soon be shutting the platform down. But if you're available, Doug, perhaps other people might still want to ask questions.
Okay,
we'll stay online.
I'll stay here until it's quiet. Thanks to everyone for coming.
Thank you. Thank you.
Thank you, Margot.
So, Doug, let me ask that quick. I meant more, for example, the coupling, when I was talking about the mixed dimensional coupling of Stokes and Darcy. That's a separate question from the mixed dimensional, but
no, you were thinking of the multi-structures that CRLA was doing a few years ago, right?
Well, both. There's the whole set of applications with, Stokes and Darcy coupled, and so
in different dimensions or the same dimension?
So both in the same dimensions and also in the different dimensions. There's some work in which fractures are treated as separate entities, and then you can have Stokes on the surface.
I see. Who's doing that?
And that also, yeah. So there are models that were, for example, Ralph Showalter with his students, that is analysis work. Okay, found a way to describe the Stokes-Darcy problem. And they were trying to use, one of the students followed up and used finite, mixed finite elements, for this coupled system. And there's work by my goodness, our French colleagues from INRIA, Jaffray and Jean Roberts. They worked on those mixed dimensional problems. Yeah. So the analytical formulation leads you to a problem where you have a jump of the fluxes, and there is anyway. It's a completely long story. So perhaps at some point we can get to connect to talk about this. It's not quite my field, but I'm aware of the work in this direction. So.
Okay, I was not aware of that work. So it sounds
Mm-hmm,
interesting.
mm-hmm,
Now that I
mm-hmm.
think about it,
Yeah.
there was some work of Quartaroni on the blood flow where he
Mm-hmm.
had connected three-dimensional models to lower dimensional models.
Mm-hmm.
I
So,
wonder if
and
that's related.
there's some work related where they, yeah, indeed, and so XFEM and people from that community also try to connect, um, yeah, and Quartarani in particular also was coupling Stokes and Darcy earlier in some earlier work. So, but I guess we'll see, right? If you have a set of Fick models, Fick elements for one side of the domain and another one for the other, perhaps the proper coupling can be done in a stable way.
I love it.
Again, defining what needs to be.
That'd be cool.
So thank you again.
Okay, it's so weird to give a talk and not see a face, not hear anything, but I guess it went well. I don't
Okay,
know. Thank you
I
so much
think
for
so. I think it